Example 611, page 153. Make sure you've opened your book and read the problem statement before we go any further. It's all about a dart gun and the changes in energy that take place when the dart is fired. So we start off with the dart gun, and it's in the cocked position with the spring compressed. So start by defining the origin of our coordinate system, and I'm going to set x equals 0 to be the point that you can't see on here yet, where the spring is relaxed, when there's no elastic energy stored. And the initial position for the whole system is that the spring is compressed by 6 centimeters at this point here. And having defined our coordinate system, we now need to define our energy system. Big red line across which no energy passes. Nothing comes in, nothing goes out. So when we look at our system, which contains the gun, the spring, and the little dart, initially nothing is moving in the system, so there's no kinetic energy. Everything's on the horizontal, so we're not worried about gravitational energy. And there is elastic energy stored up in the spring, and we can figure out what that is. It's 1/2 times the spring constant for that spring times this compression squared. So there's the amount of energy we start with that's stored up in the system. Then the gun is fired, and the dart moves out. The spring moves back to its relaxed position, and the dart is now moving with an unknown velocity v1, which is what the question asks us to find. So when we analyze the energy in the system now, we see that the spring is at its relaxed position, no extension or compression, so there's no elastic energy anymore. But the dart is moving, so there is some kinetic energy. And assuming no thermal losses or changes in internal energy or anything like that, we can say that the energy now at state 1, position 1, energy 1, is 1/2 times the mass of the dart, because that's what's moving, times the velocity of the dart squared. So the energy in its initial state, the energy in the next state of the system. And because no energy crossed this boundary, the total must remain the same, so the energy at 0 must equal the energy at 1. When we equate the left-hand sides of the equation, we equate the right-hand sides of the equation, and we end up with this expression. So now the physics is done. We've derived this equation that describes the energy in the system. The halves will cancel. Algebra will get you solving for V1, the unknown, and you would plug in the values and out would pop the answer.